Just introduce. So we are very happy to have today Yosuke Imamura from Institute of Science Tokyo, and he's going to tell us about giant Graviton expansions for the line of indices. Over to you.
Okay. Thank you for introduction. Today I will talk about giant graviton expansion. I'm Yosuke Imamura from Institute of Science Tokyo. So our institute was called Tokyo Institute of Technology, but the name has changed because it merged with another medical institute. So now the institute is Institute of Science Tokyo. Okay, this talk is based on these three papers. And M. Inoue, he is a graduate student in my laboratory. Okay. So giant graviton expansion is a formula giving supersymmetry index of finite n gauge series based on the ADS-CFT correspondence. And in this talk, we propose new giant graviton expansions for index with line operator insertions. So this is an ADS-CFT correspondence. And in this talk, we discuss the simplest version of the correspondence. So on the boundary side, we have n equal 4 super Young mills. And it has two parameters, n and g Young mills. And we consider the spacetime S3 cross S3 cross R, and R is a time direction. So spatial direction is compactified on S3. So this figure shows the S3 cross R, and this boundary is this manifold. And on the bulk side, the bulk theory is type 2B superstring in ADS5 cross S5. So the inside of this cylinder is ADS5. And on this side, we have two parameters, two dimensionless parameters. And LADS is the ADS radius, and LP is the Planck length, and G string is a string coupling. And these parameters are related by these basic relations. And index doesn't depend on continuous parameters. So it doesn't depend on these parameters, but this it of course depends on the parameter n. So this relation is important in the following discussion. And we want to compute the superconformal index. And the superconformal index of n equal 4 super Young mills is defined by this equation. And J1, so F is the fermion number, and J1, J2 are angular momenta or isometry of ADS5. And Rx, Ry, Rz are R charges that are Cartan generators of the R symmetry SU4. Of course, it is on the ADS side, it is realized as isometry of S5. Okay. And we want to introduce line operator later. And the insertion of line operator breaks some of symmetries. And so, sorry. So J2 and RZ are broken by the insertion of line operators. So we remove this factor and this factor from the definition of the index. And then we obtain the Schur index. So this is a specialization of the superconformal index. And in this talk, we consider this specialization of the index. Okay, and this Schur index is a function of two variables, x and y. But for simplicity, in the following, we sometimes set x equal y equal t to simplify the expression. Okay. Of course, this t is has nothing to do with this time t. This is just variable. And on the gauge theory side, we can easily calculate the Shua index by using this localization formula. And this function is so-called letter index, and its explicit form is given here. So this is a simple function. And chi is a character, and here there is an adjoint character of the UN gauge group. And U is n by n matrix. That is an element of UN gauge group. And this integral is integration over the group gauge group manifold that extracts the singlet contribution from this integrand. And PE is a precystic exponential defined by this equation.
Sorry,
Okay.
which are the letters that contribute to this Shur index? So one derivative,
Sorry?
one fermion, or something. Which letters contribute to the Shur index? Is it one derivative and one or two other fields?
One derivative, yeah, one derivative and scalar fields and scalar fields X and two complex scalar fields and sum of fermion fields. And I'm not sure, I don't remember if the gauge field strength contribute or not.
Thank you. But only one of the two derivatives contribute. Is this right? Yeah, okay, thank you.
Yes. Okay. And let me show you some results of some concrete calculation. So these are Shua index for small n. So U0, U1, U2 up to U6. And I show the T expansion, T series expansion here. Then we can see clear convergence in the large n limit. So in the large n limit, we obtain this one. And the important point is the finite correction is of order t to the n plus 1's power. So now let me first discuss the large n limit. So large n limit is okay. Large n limit, if you use precystic exponential, we can rewrite this series in very simple form with precystic exponential. And this simple form suggests that there exists some description by the system with weakly coupled system. And it is nothing but the supergravity description. So on the ADS side, we can reproduce this index by analyzing fluctuation modes of supergravity fields in ADS5. And this agreement, so complete agreement of this index, large n index and supergravity index provides a very strong evidence for ADS-CFT correspondence. Okay, so this is a large n limit.
Index in some suggestive form, this last large n index of supergravity. So how have we split these contributions? Should I identify these two contributions separately to something?
Here and here?
Yeah.
I'm not sure, but actually, so here I set x equal y equal t, but if you use x and y, this is actually 1 minus x plus 1 minus y minus 1 minus xy and xy. So we have three simple fraction, and I'm not sure each of these has some physical meaning
So X is the charge carried by a derivative and Y by one of the scalar fields? Or X and Y are the two scalar fields?
Yeah, X is so on the gauge theory side, X is X corresponds to the scalar field, complex scalar field X, and Y corresponds to another complex scalar field Y.
Okay, excellent.
And XY corresponds to the momentum.
Okay.
Okay, thank you.
Okay, so this is so we have nice agreement. We can see nice agreement in the large n limit, but we are interested in finite n corrections. So as I said, finite n corrections of this order. So this order. So what are objects on the ADS side giving the finite n corrections? So so according to the basic dictionary of ADS-CAT correspondence, this factor t to the nth power corresponds to operators with dimension n on the gauge theory side, or objects with energy n over L, LADS. LADS is the ADS radius. So we need to look for some objects with this energy to reproduce this factor. And actually, we can easily see that maximal giants, so giant gravitons, maximal giant gravitons, so maximal means these three branes wrapped around a large S3 in the internal space S5. So if you consider this D3 brane wrapped around this cycle, then this D3 brane has this energy. So the energy of this D3 brane, energy or mass of this D3 brane is the product of the volume and D3 brane tension. And by using these relations, you can easily check that this object has energy n over L. So this is a candidate for the objects that gives finite n corrections. And based on, yes.
In this Schur limit, do we expect black hole type entropy? Do we expect order n square entropy at energies of order n square?
I'm not sure, but I don't think so. So to reproduce the black hole entropy, I think we need a full superconformal index.
Okay, so for in this limit, maybe the order n states are all that there is. Like these branes. So I suppose the question I'm asking is the following: that often these giant gravitons indicate that you're cutting down states because you're imposing these trace relations.
Yes.
And that's going to be the role of the giant gravitons, to remove states rather than add new states.
Pardon me?
Will the role of these giant gravitons be to remove states rather than adding new states?
Yes. Remove the states corresponding to the trace relations.
Yeah. Okay.
Yes.
Great.
No, but sorry, Yosuke, this expansion that you will talk about, this giant graviton expansion, that can be done at the level of the full index also, right?
Yes.
So it will also take a similar form, but then I think there is some work by Yosuke and friends, maybe you also, where they say that kind of an expansion at n square energies does produce the black hole entropy.
Yeah. So we can there is a giant graviton expansion similar to this one for full superconformal index. So if you use that expansion, you can reproduce the black hole entropy. But
So that sense, this expansion captures everything there is about the index, right?
yeah. I believe the expansion gives the exact superconformal index. So
No, but in the case of the Schur limit, is
yes.
the role of these giant gravitons just removal of states, or does it add new states? I don't know if it's a well-posed question because at the index it's hard to distinguish
But
fermions and.
The removal should not depend on the fact that it's sure.
yeah, I'm not sure. So in the case of superconformal index, so it contains the information of so-called black hole states. That is some additional state that cannot be explained by the gravitons.
Right.
But in the case of Schur limit, I'm not sure actually.
Yeah, let me just ask once again. In the half BPS limit,
Yes.
then we know that the only thing that you have to do is remove states. Right? Because there it's just powers of Z, and the graviton doesn't impose the trace relations. The exact answer is just imposing the trace relations. So everything that you want to do. On the other hand, for 1/16 BPS, we know that we must get new states. So I was wondering whether in this limit, it was more like the half BPS or more like the 1/16 BPS. Is it just removing or also adding the Schur limit?
I'm not sure. I have not checked whether it only remove states or it can add some additional state. I'm not sure.
Become some backward states, but not a bordering state.
Right, but we know that it doesn't happen in half BPS.
Yeah, but it's not. I mean, it's not half BPS.
Yeah, so that's the question. The question is it more like half BPS?
Yeah, more like perhaps, but it will still have a little bit of.
Yeah, the question is, does it have any new state?
Yeah.
Any state that is not already present?
But for sure, Dr. The only operators are gravity.
Only graviton, right? So it's only removed. Okay.
Only graviton.
And how is this known?
Okay.
Thank you.
So this expansion is based on this observation of this formula, this relation, and here f of m. These functions are indices. So Fm is the index of the gauge theory realized on the world volume of m coincident giants. So if you wrap m D3 brane here, then gauge theory is realized, and this function is the index of that theory. So if you have a localization formula like this, and we can calculate this one. And if you substitute these functions here, then we can check that correct index, at least at least numerically. So we have done some many numerical tests, and this I confirmed this reproduced the correct index up to very high order.
So how does one analytically continue to this? I mean, you will have this single letter index X inverse, right? It will start with X inverse.
So this Schur index is symmetric for X and Y, but this is not symmetric for X and Y. So
no, I was asking that this FGG that has an X inverse piece in it, doesn't it?
Sorry.
It has X inverse, right? X inverse. X inverse, and then the positive powers of X and Y, right?
Positive value of X and Y? Sorry?
Positive powers. So negative power, X inverse.
X inverse, yes.
And then positive powers, right? Zero and constant and positive powers.
So this if you calculate, when you calculate this persistent exponential, we use, so here we have x inverse, and this corresponds to the some modes that unwrap the D brane, and to calculate persistent exponential of this x inverse, so if you use the standard formula, we have obtained this function, this fraction, and to consider x expansion, we rewrite this one in this way. Then we have negative contribution. So this function for m equal 1, this function gives a negative contribution like this. And this these terms correspond to the trace relation. So, so due to this inverse power, this contribution removes the states corresponding to the trace relations. Did I answer your questions?
Yes, yes. So if I think about it from a gravity point of view, then this x to the mn, that was the action associated with the classical part of the giant graviton, right?
What part of graviton?
Classical. That's a classical contribution, right?
Which one? Which one?
X to the mn. It's not here.
Yeah. This factor. Yes.
Yeah.
This
the
classical action.
And F is like a fluctuation around it.
Yes. This part is fluctuation. Comes from fluctuations on the D brane. Yes.
No, I mean, it seems like this power of x gets added up in x to the mn, right? X to the mn plus, or rather x to the n plus 1.
Yes.
So
n
should
plus
I
1. Plus 1 comes from
n or n plus 1?
Yeah, n plus 1. Plus 1 comes from this factor. So
Yeah,
this
from
this function, this function starts from this term. So that is the reason why the finite n correction starts from x to the n plus 1.
Okay, thank you.
Yes. Okay, so now I have a few comments.
Sorry, Yosuke, quick question. Should I think of this, if you could go back to the top slide, the capital F, should I think of that as coming from a canonical quantization of this M D branes?
Yes, I think so. So from the direct analysis of the fluctuation modes, you can straightforwardly calculate the index, at least the linearized level. So first we consider linearized action of the fluctuation modes, and we can quantize the fluctuation modes. Then we have a lot of the infinitely many harmonic oscillators, bosonic and fermionic harmonic oscillators. And by collecting all contribution of the oscillators, we obtain this result.
What confuses me is how can it be that you add some part of phase space to your theory and that ends up removing states?
So I assumed some localization mechanism work.
Okay.
So we only consider we only focus on some particular cycle, supersymmetric cycle, and we only consider small fluctuations around that cycle.
Right. I can easily imagine this happening in a localization formula. But I was hoping to get a Hamiltonian interpretation of it, that there is one part of phase space which I quantize, and then another part of phase space which I quantize, and then I add them up, something like that. So if I thought of it that way, then this capital Fm part should be adding new states, right? Because it's a new part of phase space. How does it end up removing?
So you mean, so in the definition of so Schur index, we have this operator. And so if some localization mechanism works, some fixed point of this operator, fixed points of this operator are expected to contribute
Yes.
the index. And if you look for some B3 brane configuration fixed by this action of this operator, then you will find two cycles in S5. So one is, so this S5 is, we can describe this S5 as in this way. Sorry, plus. This is plus. And we have two cycles, x equal 0 and y equal 0. These two cycles are fixed by this the action of this operator. So we expect only these two configuration and fluctuation around them can contribute to the Schur index. So we have two wrapping numbers. So actually, so this is about related to the second comment.
Okay.
So we have double sum expansion. So if you treat functions appearing in this formula, so I and f as a T series, then so T series means so we can rewrite x as Tu and y as a Tu inverse. And if you treat functions as T series, then the giant Graviton expansion becomes double sum expansion. And we have two wrapping numbers, and these wrapping numbers corresponds to the two cycles I mentioned. But if we treat functions, these functions as Y series, then interestingly, so for my greater than 1, this function becomes 0. And only fmx 0, only these functions give non-trivial contribution. And as a result, the expansion reduces to the simple sum expansion. So in this case, only one supersymmetric cycle contribute to the index, and we have simple sum expansion.
What's the relation between m sub x, this m f with the previous slide f, this and the previous slide f?
Sorry, mx and my?
No, this fxy, this fxy.
This one?
Yeah, this one, and the previous slide fxy.
Sorry, what? Are you asking what this is?
Yeah, I'm asking, is this function related to the previous slide, capital F?
So this function is the index. Sorry. Yeah, f mx my. This function is the index of the gay theory realized on these intersecting D branes. So if the number of this D brane on this cycle is my and the number of this cycle is mx, then you have umx quiver gay theory.
Yeah, thanks.
And this is the, fmx my is the index of this system. Yeah, and actually, it is much easier to calculate this one than this one. So in this talk, I will mainly focus on this reduced expansion or simple sum expansion. Okay.
So
So the
Yosuke,
Yes.
sorry, a bit tangential question if you don't mind. Going back to the full index and the giant graviton expansion that the full index admits,
Yes.
is it a priori expected that that expression, which is from the gravity side produced from quantizing giant graviton phase space, is it a priori expected that it should account for also the 116 ppm black hole states?
A priori, I think so if localization mechanism work, then it is natural that the expansion reproduce a complete index, I think. But yeah, actually, yeah, I have. I have not proved that fact, but I have no idea about other contributions.
Okay.
So I think it is convincing that the expansion gives the complete index.
Okay, I see. So even without looking at any black hole saddles or fluctuations around it, it produces this.
Sorry, in the case of
I mean, a gravity person would have thought that you would have to sum over all the saddles, including these configurations of giant gravitons, and also, if you want the black hole states,
I think
do
so.
a saddle
Yes.
point expansion around the black holes, because those are supersymmetric ones.
Uh-huh.
But somehow the second one is already included in this one.
Second one?
I mean, the black hole saddles are somehow included in this. So fast forward.
First and second mean you mean this one and this one?
No. No, I'm just making a comment. I was just saying that the gravity person would have included the saddle point contributions from the giant gravitons.
Yes.
And also black holes separately. But it turns out the second one is included in the first one. Meaning the black hole stuff is included already in this somehow. Anyway, it's not essential. We can move on.
Okay.
Yeah. So it's not really reliable. No, not impacted. It works. It's not super symmetric. Won't work very much.
Okay, next. So let me say the third comment about this. So this is a comment about this one. So double sum expansion. So this function, as I said, this function is index for the intersecting giants. And
Sorry, one question on this comment too. So you know x and Schur index is symmetric as you say between x and y, but this expression is not symmetric. So how is this? So you can either use the x1 or the y1. It's the same.
x1 and sorry. So on this side is of course the same, but this function and this function, these are not the same. So on this side we treat this function as a T series, and on this side we treat this function as a Y series. That means we consider different parameter regions. So on this side we consider for small y, the parameter region with small y, and on this side we consider the parameter region with small t, and they give a different expansion for these functions. But the answer, the total, so if you take the sum of these functions or these functions, then on this side we have the same functions. And in the case of symmetric treatment, so this one, so we have this function fmx and my. And in the case of Schur index, this function has a nice properties of factorization. So this is the index of intersecting giants, and this factorizes into 3 factors. And this factor comes from contribution from cycle x equals 0. So from mxd3 branes wrapping around this cycle. And this factor comes from the my d3 branes wrapping around this cycle. And we also have bifundamental fields arising from the open string between two cycles. And this is the factor coming from the hypermultiplet, bifundamental hypermultiplet arising from the open string connecting 2 cycles. So by using this factorization, we can rewrite the double sum expansion in this form. Sorry, I should explain these notations. So sigma x. So this is first comment. So I'm sorry, I skipped this one. So the function fm are related to the index, the original index I, by the following simple variable change. So this function f, this is the index of the giant gravitons, m coincident giants. And this one, I, is the index of the boundary theory. And they are related by a simple variable change, this one. This is because the boundary theory and the theory on giants are essentially the same. Both are the n-equal force biameters in spacetime S3 cross S1. So they are essentially the same function, but on the boundary and on the giants, the action of the symmetry generators, R charges and angular momenta, are different. So this variable change corresponds to the relation between the action of symmetry generators. And by using this variable change, we can relate this original index and this function appearing in the expansion. And we can rewrite the giant Graviton expansion by using only the function I. Okay.
Yosuke, you said that these hypermultiplets gave xy to the power mx and my.
Yes.
I think of that like a Casimir energy kind of contribution from those hypermultiplets.
Casimir energy, yeah.
These are like quantizing
Yes.
those. Yeah. Okay. Fine. Yeah. Okay.
Yes, I think, yeah. Yeah, I think we can regard this as a Casimir energy. Yeah.
Okay. Thank you.
So up to here, we discussed index without line insertion. So now we consider line operator insertion. So we consider only Wilson line operator insertion, and this is a Wilson line, and we insert here and here 2 Wilson lines, and this is a line associated with representation R, and on this side we insert a line with the conjugate representation R bar. And on the Gay-theory side, the calculation of the index is still easy. So we can calculate this line operator index by simply insert the corresponding characters. So for WR, we insert a character for the representation R. And for this line, we insert character of R bar.
So suppose we inserted just one line rather than 2.
Yeah, we can consider one line with representation R cross R bar. So I think that the answer is the same. So you can...
Sorry, not R cross R, but just one line with representation R. Could you have considered that?
That becomes 0. So we consider So in the following, we consider three cases. So these are representations. And we consider UM gauge theory. So by the charge conservation, if you consider only one insertion of only one line in this representation, the answer is just a 0.
Yeah.
Due to the charge conservation of the U1 part.
Yeah. So Yosuke, I'm a bit confused about the previous expression for the index.
Yes.
Go up a little. Up. Previous one. Yeah, here. So here, should I think of this as two stacks of branes, right? And those branes have
Yes.
their own some UM theory, UMX theory, and UMY theory.
Yes.
Right? And at the intersection, there is some bifundamentals.
Yes.
And those bifundamentals, of course, are charged under both these gauge groups. So if
Yes.
you compute the index, if you write down the index expression, it would involve a UM integral and UMX integral, UMY integral with a bunch of charged fields. So why is it that it gets factorized in this way, where you just have a UMX gauge theory on one side and a UMY gauge theory on the other side, and then bifundamentals just contribute this one?
Naively, from the bifundamental field, we have we should have this integral.
Yes.
From the bifundamental field, we have some fraction and chi of some bifundamental representation, depending on U and U dash. But I can't remember the precise form of this function, but if you calculate this persistic exponential, accidentally this becomes independent of U and U dash. So
that sounds a bit of a miracle, right? Why does this happen?
It's surprising. It's miraculous, and because it depends on the concrete expression of this function, and this is I can't remember the form, but this. I can't remember, but.
And this is only for the sure limit, right?
Yes, sure limit, only for the sure limit.
I see. Thank you.
And in the case of full index, this factorization doesn't occur, and that is one reason the calculation is difficult for full index.
Thank you.
Yes. So now we consider this index. So we know the holographic duals. So for fundamental representation, the holographic dual object is a fundamental string world sheet wrapped on this ADS2. And in the case of anti-symmetric representation of rank K, the corresponding object is D5 brane wrapped on this ADS2 and S4 in the internal space S5. And in the case of symmetric representation, this object is ADS2 cross S2. So this brane wrapped on this ADS2 cross S2 in ADS5. So let's first consider this one, R== fundamental case. So again, let me show you some results of direct calculation on the gauge theory side. And again, we have a clear convergence in the large N limit. In the large N limit, again, we have a simple expression with persistic exponential. And this part is the supergravity contribution. And this factor comes from a fundamental string. And actually, if you calculate the index of some fluctuation modes on this fundamental string, then you can reproduce this factor. So in the large n limit, we have a clear interpretation of this index. And now, again, we want to discuss finite n corrections. And from this result, we can see the finite n correction is of order t to the nth power. And so,
where is this fundamental string? Can you say it again? Where is this wrapping?
so fundamental string is here. So ADS2 submanifold in ADS5.
Oh, I see. So the Wilson line is this boundary.
Yes, yes, boundary of the world sheet are the line operators.
Okay.
And it extended along along the diameter in this figure.
But on the boundary, it's going up in time, the Wilson line?
Sorry?
It's going up in the time direction on the boundary.
Yes,
right?
yes. Time direction.
So I can think of it as one of them on the north pole and one of them at the south pole of S3.
Yes. Yes. Thank you. So again, we have this factor. So that means maximal giants objects responsible for this finite n corrections. So we should consider this configuration. So we have a fundamental string here. So this is ADS2. And we also have a giant graviton here. So that wraps around S3 in the internal space S5. So we consider this system consists of this fundamental string and D3 brane. Actually, we need to consider two configurations. In the first configuration, we have fundamental string and D3 brane. And this fundamental string doesn't end on this D3 brane. And in the configuration 2, on this side, this fundamental string ends on the D3 brane world volume. And these two configurations gives different contribution to the index. And based on this, based on the analysis of the fluctuation modes on this configuration and on this configuration, we can propose this giant Graviton expansion for the line operator index. So this on this side, so this one is a fluctuation of F1, so fundamental string, and Fm is the same as the previous one. So this is, you can get this function f from the standard index, original index by this variable change. But on this side, we have two half strings, semi-infinite strings. So the fluctuation modes are different from this one. So the index is different. So by using this one here, and from the D3 brane, we have this one. This one is the line operator index on the giant, because these two endpoints of the fundamental string plays a role of line operator. So in the expansion, we have the line operator index here, and this is related to the line operator index on the boundary by a simple variable change. And we can check that this expansion works. This expansion gives the correct answer up to very high order by numerical check. And so now let me skip this one. So this is for T expansion case, but let me skip this one. So next, let me consider the anti-symmetric representation. So line insertion of line with anti-symmetric representation AK. This is a rank K anti-symmetric representation. in this case, the dual object is D5 brane. So D5 brane wraps on ADS2 cross S4. And this S4 is a subspace of this internal space S5. And this angle, the radius of this S4 is determined by this relation. So this angle is related to the rank K of the anti-symmetric representation. So we expect in the large N and large K limit, the supergravity mode in the bulk and fluctuation modes on this D5 brane contribute to the index.
If K is very small, we can think of this D5 brane as S4 as being very small sphere, and therefore just like a fundamental string. Is this right?
Yes. Right. So on this D5 brane, there is electric flux. So this has charge of fundamental string. Thank you. So let me show you some results of the calculation on the gauge theory side. So here we consider large N limit. I have already taken the large N limit, and K is so for small K, the results are these series. So if you increase the K, we have some limit, and if you send the N and K, both N and K to infinity, we have this result. So again, we have a simple expression with persistic exponential, and this part is a supergravity contribution, and this part is a D5 brane contribution. So in the large N and large K limit, we have clear interpretation on the gravity side. And now we are interested in the finite K correction. Let's first consider finite K correction before finite N correction. So we consider the case with N is infinity, but K is finite. Then finite K correction is of order T to the K plus 1th power. So we want to reproduce this contribution as something by the some object on the ADS side. So to reproduce this factor, we need some object with this energy K over LADS. And we can easily check that disk D3 brane ending on the D5 satisfy this condition. So, so this is D5 brane. This is a cross section of D5 brane. This is S4. And we can consider giant graviton wrapped around large S3. So we can consider giant graviton wrapped around large S3.
Sorry, Yosuke. So when you say large M, large K limit in the previous slide, is it being taken with K by N fixed?
N fixed. So we first take the large N limit. Then after that, we take the large K limit.
Okay, no, but if one does that with K over N fixed, K by N fixed.
K over N fixed.
Because
that's
natural, right? With the theta angle, that angle depends on K over N, right?
Yeah. So K over N fixed. And if you take this limit, then you get the same result.
I see. So it doesn't depend on where this D5 brane sits.
Yes. It is independent of this angle theta, this theta.
Okay. Fine.
Yes. Yeah, that is interesting point. And so to reproduce finite K correction, we want to get some objects with this energy. And we can consider, so this is D5 brane, and we consider, so giant graviton wraps around this large S3, but we can consider D3 brane wrapped on this part.
Sorry,
So
one
this
more
is
question. Sorry,
yes.
one more question. So it feels like this picture suggests that the R symmetry is somehow broken
R symmetry.
because you pick some pole point.
Yes. So R symmetry. So originally we have SO6, but this is broken to SO5.
That happens already when you introduce the line operator, is it? Yeah, I guess.
Yes.
Yeah, okay. Thank you.
So in the case of fundamental string, we also have this broken symmetry.
Yeah, thanks.
Yes. So in this slide, this looks like a segment, but this is actually a three-dimensional disk. And if you calculate the volume of this three-dimensional disk, and if you take the ratio of this volume of disk and the volume of S3, then this is the same as this ratio. So that means, so if you consider a whole giant graviton, it has energy n, but if you consider this part, it has energy k, so k over L. So this is a candidate object for the objects corresponding to this finite k collection. So we want to calculate the index coming from this D3 brane. And actually, the index, this index has been calculated by this paper, in this paper, and this is called half index because this D3 is so D3 brane is a three-dimensional disk, and this is the same as it is the same as a hemisphere, three-dimensional hemisphere. So this index is index for the hemisphere, so it is called half index, and we can calculate by using this localization formula.
So what is M in this case?
M. So we need to sum up all contribution with different M. So M runs from 0 to infinity.
But the K dependence is very simple. It's just the energy.
Yes. So this is a giant Graviton expansion, and K appear only here. And this part is a half index, and this is independent of K.
Okay.
So we have already checked that this gives the correct answer. This expansion reproduces the answer obtained on the gauge theory side. So this is a expansion, giant Graviton expansion for n infinity and k finite. Okay. And we can generalize the results to finite n. It is very easy. So we consider, so to reproduce a finite k collection, we consider D3 brane wrapped on this part. But if n is finite, we should also consider the D3 brane wrapped around the other side of this three cycle. As a result, we obtain this double expansion. So M is the number of D3 brane wrapped on this part, and M dash is the number of D3 brane wrapped on the other part. And this F of M comma M dash, this is the index of the theory realized on this system. So this is a quiver gauge theory with gauge group UM and UM dash. And of course, it contains a contribution from open string here. So this is a concrete expression for F of M and M dash. So this is obtained by this localization formula. And corresponding to two gauge groups, we have two integral. And this F tot consists of three parts, and two of them are contribution from vector multiplet living on this part and living on this part. And this middle line is a contribution from hypermultiplet coming from this open string. So this is so this part, the boundary is a three-dimensional manifold. So this hypermultiplet living on three-dimensional space-time, and we can easily calculate the data index for this part, and we can calculate by using this localization formula, we can get this function f.
So Yosuke, in this calculation, the d5 brane doesn't fluctuate, doesn't contribute to any volume determinants.
In this calculation, we assume that this d5 brane is a rigid object.
But in the gravity part, in the earlier large N part, you had fluctuations of the d5 brane.
Yes.
Can you go back, sorry?
So yeah, this part. So to reproduce this, we consider fluctuation of d5 brane.
And then this d3 brane can also rotate, right? Depending on where it ends. Is there some integration done accordingly?
Sorry, d3 brane fluctuation?
No, I mean it can move around the d5 brane.
Yes. So we of course include such mode of the rotation, and it is contained in the calculation of this function.
I see. So what is that? What kind of contribution is that?
Sorry. So this function, this is a function. This is a letter index for this D3 brane. And you have, so if you expand this letter index, you have, for example, x inverse y. And this corresponds to the rotation mode.
I see.
Because
it should be a zero mode, right?
Yeah, zero mode, yes. So
because it's x and y homogeneity is 0.
Yes, x1 if you rewrite this function by t and u, then this is tu minus 2 minus square. So sorry, no t. So t to 0. So this zero mode, this is zero mode. Yeah.
Okay.
Yes. So this in this case, again we confirm by direct numerical calculation, and we confirmed that this expansion correctly reproduced the answer results obtained on the gauge theory side. Yes. And let me skip. So yeah, let me give a short comment. So this expansion can be this is the same expansion with this one. So this part is f of m and m dash. And again, we can get this function by a simple variable change from the interface index. And the interface index is defined as some partition function on this system. So here, this is not a line, but the interface. So on this side, we have UM gauge theory, and on this side, we have UM dash gauge theory. And this is a domain wall. These are domain wall. And we can define interface index as a partition function of this system. UM um dash. And this expansion relate, so this expansion on the right-hand side, we have line operator index, but on the left-hand side, opposite. So left-hand side, we have line operator index, and on the right-hand side, we have interface index. So this expansion relates line operator index and interface index. And the inverse relation also discussed in these papers by Hatsuta, Rin, Okazaki, and the opposite relation also seems to hold. So this is very interesting. And we can also consider surface insertion. And in that case, surface index can be expanded by surface index themselves. Okay. So this, okay, let me skip this part. And finally, let me comment on the symmetric representation. So the symmetric representation, the Wilson line of symmetric representation corresponds to D3 brane wrapped on ADS2 cross S2 in ADS5. But disappointingly, the result on the gauge theory side. So let's first consider large N and large K limit. And on the gauge theory side, we can calculate the index. And on the gravity side, ADS side, we expect this is reproduced by taking account of D3 brane fluctuation modes. But results these two results on the gauge theory side and gravity side do not match. I don't know why they do not match. Yeah, this looks like this are very similar. If you rotate this expression by 180 degrees, then you can get something like this. But of course, these two are mathematically completely different. So I have no idea at present why these two do not match. But even so, we can still consider finite N and finite K corrections on the ADS side. So finite N correction, to explain finite N correction, we need objects with this energy, and we can expect maximal giants again gives a finite N contribution. And for finite K corrections, we need to look for objects with this energy, K over L. So what are these objects? And we found such objects. So if you consider D1 brane, so this cylinder is D3 brane, so ADS2 cross S2. So this cross section is S2. And if you and this radius of this S2 is determined by this relation, depending on K. And if you consider D1 brane along the diameter of this S2, and if you calculate the mass of this D1 brane, then you can show that the energy is just K over LADS. So this D1 brane is a strong candidate for the objects giving the finite K corrections. But of course, we need to understand large N and large K limit first to match the results between the gauge theory side and gravity side. Okay, so now let me summarize my talk. So we proposed giant graviton expansions of line operator indices for fundamental representation and anti-symmetric representation. And they pass highly non-trivial numerical tests. And there are many directions for the future. And for example, more general representations. And we can also consider other types of extended objects. And we can also consider other theories other gauge groups and other space-time dimensions. And I also commented on a puzzle. So we have not succeeded in reproducing the index for symmetric representation by the holographic realization with a D3 brane. The results do not match at all, even in the large N and large K limit. So before we attack finite N and finite K corrections to this index for symmetric representation, we need better understanding about the relation between this Wilson line and D3 brane configuration. Okay, that's all. Thank you very much.
Okay, are there any more questions?
So Yosuke, could you remind us why the anti-symmetric representations blew up into D5 branes while the symmetric into D3 branes? What was the difference between? It was
difference.
Meyer's effect blowing them up, right? But why
Yes. So both configurations okay. So both are realized by the Meyer's effect. And in this case, so the size of it, so in this case, size of S4 is a function of, so N over K, so theta D5. So some function of this K. And in the case of S4, at K equal N, this angle becomes pi. And that means, so we have a symmetry between K and N minus K. So this is a case for unsymmetric representation. So this is expected to correspond to unsymmetric representation. But in this case, so this S2 is in ADS5. So there is no upper limit for the radius. So that is the same for the rank of the symmetric representation. We have no upper limit for the symmetric representation. So this is very naive explanation for the correspondence.
Why couldn't it have blown up into an S2 on the S5? Why couldn't the anti-symmetric guy have blown up into an S2 on the S5? Why S4?
S2 and S5.
Why has it blown up into D5 rather than D3 branes?
So Meyer's, so we have on D5 brane we have electric flux to reproduce the fundamental string charge. Then this can couple to the so by the Wess-Zumino term SD5. So this D5 brane can couple with this Ramon four-form field. So by the Meyer's effect, you can form this kind of configuration.
Thank you. Yeah. One more question. Sorry, it's
yes.
A very general question. Right at for the beginning part of your talk, why
yes.
did only maximal size giants contribute to expansion? Why not giants of every size? Or is the idea that the fluctuations
I see.
Taking those into account?
Yes, so we only consider this maximal giant, but we also consider the fluctuation around this one. So for example, For example, if you expand this letter index, you can see there is a term corresponding to deform this giant sorry, this is not a good figure. So this is a maximal giant. And in this, so we have, for example, we have X inverse here. So this mode, the corresponding mode is something like this. So this is unwrapping mode. So this means if you include this term, you include some smaller configuration near the maximal giant. So in this way, all fluctuation modes are included in this letter index. So
But you're only including small fluctuations. So the guy that's
yes,
halfway,
yes.
half the size of the sphere is not included, right? Somehow.
Yes. So probably to answer your question completely, I should prove the localization mechanism works, and the all contribution localized on this along this specific cycle.
Okay.
But yeah, I haven't done it.
Oh, thank you.
So, sorry, you said there is a unwrapping mode, but like according to your analytic continuation procedure,
Yes.
but the statistic exponential of x to the minus one starts from minus x. So like the charge increases rather than decrease.
Yes.
Well,
Yeah, that's right. Yes. Yes. So
Yeah.
Yeah, physically is correct. Yeah, it's magic. It's like so.
yeah, I don't have good explanation for this analytic continuation. So this is a kind of mathematical procedure, and this is a physical explanation for this term. And yeah, I agree that this explanation and this explanation looks different. And yeah, I use this one as simply as a mathematical prescription. Yeah.
thank you.
Sorry, I'm sorry. Yeah.
More questions? If not, let's thank Yosuke again for a wonderful talk.
Thank you very much.